Okay, good evening, everybody. Welcome to day 2 on week 5 of the semester. Right now, we are going to cover the topics of section 3.5, which is the concept of the mole. So in chemistry, whenever we're counting atoms or we're counting molecules, we utilize the mole as our basic unit to be counting, okay? So the mole is what we know as the unit that we utilize for any item that is chemically based. What does that mean? We can be counting atoms, we can be counting molecules. And as you can see here, the mole or 1 mole is known as Avogadro's number. And by definition, Avogadro's number means that 1 mole of an element, 1 mole of a compound is going to be 6.022 times 10 to the 23rd items. So if we have elements, those items are going to be atoms, but if we have a compound, those items are going to be molecules. Now, you can see in the bottom of the slide that these are images of 1 mole of the following elements. So in the first image, you have 1 mole of zinc. In the second one, you have 1 mole of carbon. Then we have 1 mole of magnesium. And lastly, we have 1 mole of copper. Now, because we have 1 mole of each, that means that 1 mole of an element equals 6.022 times 10 to the 23rd atoms. Of the element. So that means that the first image where we have 1 mole of zinc, that's going to equal 6.022 times 10 to the 23rd atoms of zinc. For the second image where we have 1 mole of carbon, that is going to equal 6.022 times 10 to the 23rd atoms of carbon, so on and so forth, okay? Now, you guys can see here that there's this very interesting picture, and you may be like, oh, okay, what the heck is that? So you can see that this says Avogadro's number guacamole, okay? Anybody else shops at Trader Joe's? That's my favorite shopping store. Put a 1 in the chat if you like to shop at Trader Joe's. There you go. There's some people with me that like Trader Joe's. Well, at Trader Joe's, one of the interesting things, and the nerd in me couldn't resist to put this image, because when it comes to Trader Joe's, you guys, you can see that here in the corner for the packaging of pre-made guacamole, there is the image of a person. Who is this person? Can you guess? Who's this guy? It just says, let's party, arriba. But what would you guess? Since in the word guacamole, there's the word M-O-L-E, mole. Exactly, that's Avogadro's. So again, I couldn't resist. The nerd in me was just like geeked out. It's like, oh, this is just funny that they put in guacamole the picture of Avogadro. There's also like a silly chemistry joke about avocados and guacamole, and because it's a mole. Anyways, I don't know the joke because it's pretty bad, but I just found amusing that they put the picture of Avogadro's on the guacamole at Trader Joe's guacamole packaging. But in general, what do we need to know when it comes to these conversions? And we are talking about the units of mole. One of the things that we need to learn how to do is, how do I find, if I'm given moles, how many atoms of an element I have? Or if I'm given molecules, how many moles of a particular compound I have? Well, with that, we are going to utilize as our conversion factor Avogadro's number. So here we have the following problem. It says, how many carbon dioxide molecules are in 0.50 moles of carbon dioxide? So for this problem, we are given moles of a compound. What we need to find is going to be molecules of that compound. As you can see, the conversion factor that we need to change from moles to molecules is going to be Avogadro's number. And as I just stated previously, this conversion states that 1 mole, and in this case of a compound, is going to equal 6.022 times 10 to the 23rd molecules of that compound. So let's set up this problem. When it comes to this problem, we are going to write what is given to us. 0.50 moles of CO2. Our conversion factor is going to be Avogadro's number. Since we need to cancel the unit of moles, in the bottom, we're going to put 1 mole of the compound, which is CO2. On the top, we're going to do 6.022 times 10 to the 23rd molecules of CO2, because remember that that is our conversion factor. Now, in dimensional analysis, remember that the units are always going to cancel diagonally. So that means that the mole of CO2s are going to cancel with moles of CO2. So in this process, all I have to do is enter in my calculator 0.50 times 6.022 times 10 to the 23rd, and then I get my result, okay? So when we do this, okay, we're going to get a calculator display, okay? Can anybody put in the chat what would be the calculator display for this? If we take 0.5 and we multiply it times 6.022 times 10 to the 23rd. Thank you, Maria. So when we get the value of 3.011 times 10 to the 23rd, we need to keep in mind the number of sig figs that were given to us. So sig figs are coming back for this little section. So because we were given 2 sig figs, we need to round that value of 3.011 times 10 to the 23rd to 2 significant figures. So that means that our final answer is going to be 3.0 times 10 to the 23rd molecules of CO2. So you may be wondering, why is it that we need to calculate all of this? In the laboratory, we are not going to have experiments to do this, but at times as a researcher, you are interested in the number of atoms that are going to be produced or the number of molecules that are going to be produced, depending on the type of experiment that you have. So this is an important calculation to know. So at this time, let's do some practice problems. So I'm going to give you guys 3 minutes to do the 2 practice problems that we have in the bottom. Problem number 1, we need to find the molecules in 2.00 moles of H2O. So this is going to be similar to the problem that we just did. And then the one below, we have to go from atoms to moles. One thing that I'm going to specify here, let me just write notes. If we are going from moles to molecules, okay? From moles to molecules, like the problem we did, we're going to multiply by Avogadro's number. But if we're given molecules and we need to find moles, like in the second example, understand that we're going to divide by Avogadro's number, okay? So again, I'm going to give you guys 3 minutes. Please work on problems 1 and 4 from the in-class worksheet. One more minute. Great, let's go over the answers of these 2 problems. So in the first problem, we're trying to find out how many molecules of water we have in 2.00 moles of water. So because 2.00 moles is what's given, that's what we're going to write, 2.00 moles of water. And in order to do this conversion, we have to multiply by Avogadro's number. So this is going to be 1 mole of water equals 6.022 times 10 to the 23rd molecules. So MOLEC is going to be my shorthand for molecules. And in the process, we're going to cancel the units of moles of water. And then in our calculator, we're going to do 6.022 times 10 to the 23rd times 2. So we get a calculator displayed that it is 1.2044 times 10 to the 24th. How many sig figs do we need to show in the result? Let's put it in the chat. How many sig figs? Great, 3. So we're going to round our result to 1.20 times 10 to the 24 molecules of water, okay? Put a 1 in the chat if you got that result. Let me see how many people got it. At least Isaiah and Kiyomi. Vanessa got it, Guadalupe got it. Great job, you guys. Make sure that you practice as we are practicing along. Let's do the second problem. in which now we are given 7.46 times 10 to the 23rd atoms of carbon, and we need to find how many moles is that equivalent to. So we're going to write 7.46 times 10 to the 23rd atoms of carbon. And in order to change this to moles, we're going to divide by Avogadro's number. 6.022 times 10 to the 23rd atoms of carbon equals 1 mole of carbon. So when we cancel, atoms of carbon are going to cancel each other. So our final unit is going to be in moles of carbon. So when we do this, 7.46 times 10 to the 23rd, we divide it by 6.022 times 10 to the 23rd, and we find a calculator displayed that it is 1.23879110, so on and so forth. So we need to round that to 3 sig figs because those are the significant digits that we have in the coefficient of the unit given. So our final answer in terms of the moles of carbon that are given by those atoms is going to be 1.24. So put a 4 in the chat if you got number 4 correct. Excellent, great to see that. Now, depending on the calculator that you guys will be using this semester, please be careful when you're entering Avogadro's number, especially if you guys are doing a division. Because the issue is that if you don't put Avogadro's number at times in parentheses, your calculator may give you an exponent that is like -46 or -47. And understand that that is an issue in entering the answer. So you should not have, large negative results when you're doing these mathematical operations, just because it's not in conceptually what we're trying to accomplish. So please be careful when you enter these numbers in your calculator. If anybody has issues with utilizing your calculator, please feel free to come to office hours or hang on after we finish the class, and I'll be more than happy to help you how to utilize your calculator, okay? Any questions on doing conversions between given moles and we're finding atoms or molecules, or if you're given atoms and molecules and we need to find moles? Great, since there are no questions, then let's talk now about molar mass and what does that imply. When it comes to molar mass and calculations, understand that mole quantities, when we look at them visually, and these are different beakers with different compounds, we can actually see that as the number of atoms in our chemical formula are increasing, the amount of solid is increasing. And that is because molar mass takes into account the atomic mass of every element in the molecule. And when it comes to how do we use it as a conversion, understand that we already learned that 1 mole of atoms is going to equal 6.022 times 10 to the 23rd atoms of that element. But as we can see here, that is also related to the grams of a particular element, okay? Where do we get this number that is 12.01 grams? Carbon atoms from the periodic table. This number that we see right here is going to be what we call the molar mass for an element. So when you look at the periodic table, atomic mass has units of AMU, but molar mass has units of grams per mole. So what this is referring to is that in 1 mole of carbons, there's going to be the atomic mass of carbon, 12.01 grams. That's what it is equivalent to. That's why molar mass has units of grams per 1 mole. Now, why is that important? Well, we also need to learn conversions of how to go from moles to grams. And this is one of the typical conversions that we do when we're doing chemistry research. The reason is, as we move along, once we get to chapter 5 and we learn about reactions, understand that reactions, when you look at the relationship between the components of a reaction, we always look at mole quantities. But the top loading balances that we have in the laboratory are not measuring specifically mole quantities. What we can measure is grams. So that's why it's so essential that we're able to convert from moles to grams, so we're able to weigh out the amount of a particular element or compound that is required in our reaction. So let's do some practice problems now, in which we are going to be specifically doing a conversion between grams of something given and moles. So we can see the following example. It reads, a box of table salt. Give me one moment. So in the following problem, it reads, a box of table salt, in other words, sodium chloride, contains 737 grams of sodium chloride. How many moles of sodium chloride are in this box? Well, we can see in the corner that whenever we're doing a conversion between grams of a compound or grams of an element, as you can see in the top, and we're trying to find moles of a compound or moles of an element, our conversion factor is going to be molar mass. So let me just label this. So this is our conversion factor. So the molar mass, and that is going to be in grams per mole. And when we are doing this, understand that, like in the example that we have, since we are given grams of compound and we're trying to find moles, understand that we're going to divide by the molar mass. If we're given moles of compound and we're trying to find grams, we are going to multiply by the molar mass, okay? So let me just make those notes here too. If we're going in this direction of our conversion, we are dividing by the molar mass. If we're going in this direction, we are going to multiply by the molar mass. So in the problem that we have in hand, we specifically have to go and we have to divide by the molar mass. So before we write the amount given, let's actually generate our conversion factor. Let's just first calculate molar mass for our compound. If you had an element, understand that your conversion factor is already given in the periodic table, but if you have a compound, we have to calculate it. So since our compound is NaCl, the way that we do this is that we say we have a sodium ion and we have chlorine. Since they have subscript of 1, that's what we're going to place right there. Then I'm going to utilize the values that are in the periodic table in your textbook. So sodium has a molar mass of 22.99 grams per mole. Chlorine has an atomic mass of 35.45 grams per mole. So when we multiply by 1, we get the same value out. And all we have to do as the last thing is just to add these two numbers. And this is going to be 58.44 grams per mole. So once you have calculated the molar mass for your compound, now you are set up to do the problem. So we write the amount given, 737 grams of NaCl. Then utilizing dimensional analysis, because I want to cancel the grams unit, I'm going to put in the bottom 58.44 grams of NaCl. And on top, what that equals to, which is 1 mole of NaCl. The units of grams of NaCl cancel with each other. So then our result is going to be in moles of NaCl. And when I divide these two, 737 divided by 58.44, I find a calculator display that is 12.6112, so on and so forth. So I need to round my calculator display to 3 significant figures. So my final answer is going to be 12.6 moles of NaCl. Any questions doing calculations between moles and mass or vice versa? If there are no questions, then let's practice. As you can see here, we have 3 problems. I'm going to give you guys 3 minutes to calculate either the grams, like in the first question, second and third question, but the problems that we have in the in-class worksheet can go the other way around, in which you can be given grams and then you have to calculate moles. So these problems are going to be in the other direction from the example that we just did. So I'm going to give you guys 3 minutes to complete these problems. Again, we're finding grams, but we were given moles. One more minute. Okay, let's get started on these problems. So on each of these problems, we were given moles, but we needed to find grams, okay? So in the first one, how much do 8.13 moles of neon weigh in grams? So we are given, in this case, moles of an element, and we need to find grams of an element. So that means that here we're going to write 8.13 moles of neon. And in order to change it to grams of neon, we're going to multiply by the molar mass of neon. In 1 mole of neon, looking at the periodic table, we see that there are 20.18 grams of neon. So the units of moles of neon cancel. And then when we multiply 8.13 times 20.18, we have a calculator display of 164.0634. So when we round it to 3 sig figs, then we see that is 164 grams of neon. Put a 1 in the chat if you got 164 for the first problem. Great. Let's move on to the next problem, which is given 0.345 moles of chlorine gas, how many grams do you have? Well, in this case, let's just write what is given to us. 0.345 moles of chlorine gas. Now, I want to remind you guys that when it comes to certain elements, elements sometimes are found as diatomic molecules. And whenever you see the word chlorine gas or molecular chlorine, because chlorine is one of those elements that is diatomic, what we are referring to is actually Cl2. So if you forget that fact, then the answer is going to be different from the real one. So the other molecules from the periodic table that are diatomic are hydrogen, nitrogen, oxygen, and then your halogens: fluorine, chlorine, bromine, and iodine. So whenever you see molecular hydrogen, molecular nitrogen, molecular oxygen, molecular fluorine, or chlorine or bromine or iodine, or you see a state of matter, chlorine gas, hydrogen gas, nitrogen gas, oxygen gas, understand that the only ones that have states of matter that are not gas is going to be bromine and iodine. Most of the time, bromine is found as a liquid and iodine is found as a solid. But whenever we see those hints, remember, oh wait, this is a diatomic element. So when I do, the molar mass is going to be a little bit different. So in this conversion, understand that we are looking at the molar mass of 1 mole of Cl2. So that means that the 35.45 of chlorine, we have to multiply times 2. That is 70.9 grams of Cl2. And we multiply that times 0.345. We get a calculator display of 24.4605. When we round it to 3/6, then our final answer is 24.5 grams of Cl2. Questions about number 2? If number 2 makes sense, put a 2 in the chat.
So
Excellent.
are you saying that if something says gas, like chlorine gas, that's like a signal that it would be Cl2 as opposed to just going to straight chlorine?
Correct. So whenever you see
yeah.
chlorine gas, so out of these diatomics, the only ones that are gases, let me just use my highlighter tool to specify which ones are a gas, which ones is a liquid, and which one is a solid. So let's say that the problem would have said same thing, but it would have said liquid bromine. Then you know that you're talking about Br2, or solid iodine. So if you don't have the state of matter with these diatomic elements, and you have the word molecular, it symbolizes the same thing, that we're talking about the diatomic molecule. It's just something to be aware of. It's just because these elements, when we see them in nature, they are diatomic, meaning that 2 atoms are together. So when it comes to the ones that are gas form, is hydrogen, nitrogen, oxygen, fluorine, chlorine. I'm just going to underline Br2 because Br2 can be found in gas form too. When it comes to the ones that are liquid, Br can be found also as a liquid. And then lastly, when it comes to the one that is found as a solid, there's going to be I2. So remember, I just make you guys aware of this because I find sometimes that in quizzes or in exams, people just look at the word chlorine and forget to keep on reading in the question. And then they're like, why did I get it wrong? Well, because you didn't complete reading the whole sentence. So please be aware whenever you have these atoms, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, and you have that keyword, the state of matter, solid, liquid, or gas, or the word molecular, that has to click in your brain that we're talking about the diatomic. Then let's move on to the third problem, which is we are given 1.11 moles of nitric oxide gas. And we need to find how many grams would you have. So nitric oxide is actually one of those common names that you guys need to know for a certain list of covalent compounds. What is the chemical formula of nitric oxide? Let's put it in the chat. Excellent. Capital N, capital O. So we write 1.11 moles NO. Let me just put it a little bit to the top. And then we have to use as a conversion the molar mass of NO. Remember, we need to calculate this. So molar mass of NO is going to be the mass of nitrogen, which is 14.01, plus the mass of oxygen, which is 16.00. Since we only have one of each atom, then we can just add the 14.01 for nitrogen plus the 16.00 for oxygen. So this gives us a value of 30.01 grams per mole. Okay, so in the bottom, we put 1 mole of NO. And then on top, we put 30.01 grams of NO. The units of moles cancel. And when we do 30.01 times 1.11, we find 33.31111 grams of NO. But remember, we were given 3 sig figs, so we're going to round to 3 sig figs. So our final answer is 33.3. Put a 3 in the chat if number 3 makes sense. Excellent. There's one more calculation that we need to know. And that is, if you have given mass and you need to find all the way to atoms, it could be for an element or it could be for a compound, and vice versa. If you're given atoms, then you can find grams of that element. If you're given molecules, you can find specifically the grams of that compound. So here we have 2 problems. So far we have done basically just grams to moles. We have done moles to atoms, and now we're doing the whole thing. So as you can see, like in the first problem, we are given atoms of an element. So in problem 1, we are given atoms of an element. What we need to find is grams of an element. As you can see, you're going to use 2 conversion factors. The first conversion factor is going to be Avogadro's number. The second conversion factor is going to be the molar mass of that element. Understand that the same process will be if you're given molecules and you need to walk all the way to grams of compound, okay? Now, as we can see in problem 1, let's just write the number that is given to us. 3.01 times 10 to the 22nd atoms of magnesium. So in the first conversion factor, I'm going to use Avogadro's number to find the moles of the element. So let's put it in the chat. Are we multiplying by Avogadro's number or are we dividing by Avogadro's number? So to get to moles of an element, are we going to multiply by Avogadro's number or are we going to divide? I agree with Maria. I agree with Katie and Vanessa. Great job, you guys. So we're going to divide by Avogadro's number. So we're going to do 6.022 times 10 to the 23rd atoms of magnesium. And then on top, we're going to say 1 mole of magnesium. And we took care of the first conversion factor. Okay. Let me use my highlighter tool. Then, as you can see, we have a second conversion factor to find those grams of the element. And that is going to be coming from the molar mass of the element. Where do I find that number? Let's put it in the chat. Where do we find that value? Great. Thank you, guys. Exactly, in the periodic table. So when I go to my periodic table, I'm going to utilize the molar mass of magnesium. So I'm going to say 1 mole of magnesium in the bottom because I'm trying to cancel the unit of 1 mole. And then on top, the molar mass in grams of magnesium, which is 24.31 grams. So when I look at the cancellation of my units, atoms of Mg cancel with atoms of Mg, moles of Mg with moles of Mg. So everything in the result is going to be in grams of magnesium. So when I do this, I'm going to take 3.01 times 10 to the 22nd. I'm going to multiply it times 24.31, and then I'm going to divide it by 6.022 times 10 to the 23rd. Okay, so I got a calculator display of 1.21509, so on and so forth. Because I'm given 3 sig figs, I need to round my answer to 3 sig figs. So my final answer is 1.22 grams of magnesium. As you can see in number 2, we have the same process, but what we're given is a compound. How do you know that you're dealing with a compound? Because of the name. Here we have nitrogen dioxide. So what is the chemical formula for nitrogen dioxide? Let's put it in the chat. Thank you, Kiyomi. Thank you, guys. Great job. So nitrogen dioxide is NO2. So knowing your chemical formulas, it is essential for the second exam, okay? So at this time, I'm going to give you guys 2 minutes to do problem 2. One more minute. Okay, let's solve problem 2. We're going to write in the numbers given, which is 14.72 grams of NO2. Now, here in this work, so for number 2, oh, let me use a different color. So for number 2, since we were given grams and we need to calculate molecules, as you can see, we are going into doing these conversions in this direction. We still utilize the 2 conversions of molar mass and Avogadro's number, but let's use the molar mass as our first conversion, okay? So the molar mass of NO2 is going to be 16.00 times 2 plus 14.01. So when we do that, we see that the molar mass of NO2 is 46.01 grams per mole. So when we're doing our conversion, in the bottom, we're going to put 46.01 grams of NO2, and on top, 1 mole of NO2. Then we proceed to do the second conversion. So this is the first conversion. In the second conversion, we're going to use Avogadro's number. So in Avogadro's number, we're going to put in the bottom 1 mole of NO2, and on top, we're going to put Avogadro's number, 6.022 times 10 to the 23rd molecules of NO2. When it comes to the cancellation of units, grams of NO2 cancel with grams of NO2, moles of NO2 with moles of NO2. So overall, our final answer is going to be in molecules. Remember that my shorthand for molecules is MOLEC. So what we find is that we take 14.72 times Avogadro's number, 6.022 times 10 to the 23rd. We divide that by 46.01, and we get a result that is 1.9266 a series of numbers times 10 to the 23rd, and we need to round it to 4 sig figs. So this is going to be 1.927 times 10 to the 23rd molecules of NO2. Put a 2 in the chat if you were able to get that result for the second one. No problem. Hey, that's part of the problem, learning. But put a 2 in the chat if at least it makes sense, the working or the process of how we go from grams to molecules. So in essence, when we're doing these problems, let me just finish highlighting this so in the notes make sense. So this is the second one. This is the first one right here. Maybe let me use a different color. This is this one. This is this one. Questions. Doing the conversions between mass to atoms or molecules or vice versa. since there are no questions, make sure that you practice. I will be posting by tomorrow lab 4B, or sorry, lab 3B. Also the chapter quiz for the second part of chapter 3 that we didn't get to cover in exam 1. So be aware that those assignments will be due next week towards the end of the week. So this is the last topic that we're covering in chapter 3. Now we are going to move on to talk about the topics of chapter 4. And chapter 4 is titled An Introduction to Organic Compounds. So when it comes to organic compounds, understand that these are going to be covalent compounds that have at the highlight of the compound carbon atom bonded to other nonmetals, okay? So in section 4.1, we talk about the simplest hydrocarbon that is out there, which is known as an alkane. The reason why alkanes are known as hydrocarbons is because in their chemical formula, they only have hydrogens and carbons. So for these organic compounds, the only thing that we have is going to be single bonds between carbon atoms and single bonds between carbon and hydrogen atoms within the formula. Now, how do you know the general formula for an alkane? Well, here you have the general formula for alkane, which defines them as CnH2n plus 2. What does that mean? N is just going to be a whole number, which can go from 1 to infinity. But in this class, we're only going to focus when n equals 1 to n equals 10. So when it comes to this, if n equals 1, then that means that is C1, and for hydrogen, the subscript is going to be 2 times 1 plus 2. So overall, the simplest alkane is going to have a chemical formula of CH4, okay? Now, alkanes are going to be formed by continuous chains of carbon atoms, and they are called saturated hydrocarbons because they contain the maximum number of hydrogen atoms that the molecule can hold. So this table is actually from a different reference book, but in your textbook, you have a similar table on page 125, okay? It's just that the one that is on page 125 gives you the Lewis structures for alkanes. So let me just write that. So at page 125 in your textbook, you have the Lewis structures for alkanes, but it's the same concept. It tells you the number of carbons in the first 10 alkanes. This table gives you the prefix because in organic chemistry, the number of carbons is going to be assigned a specific prefix. And then it gives you the alkane name, you have the molecular formula, and then you have the structural formula. So we can see here that it is very important that when it comes to this, you guys memorize the following. The number of carbons, the prefix that is attached to. Because in this chapter, we're going to learn to name certain organic compounds. And if you know what is the prefix and that is attached to the number of carbons, naming organic compounds is going to be an easier task. So as we can see here, our smallest alkane, as you can see, is CH4, as I illustrated by putting the digit of 1 as n equals 1. And then we can see that that is called methane. That's one of the things about organic chemistry. If we're talking about alkanes, the ending will tell you if you have an alkane because it's going to end in ane. If you have 2 carbon atoms, the prefix is F, and the alkane of 2 carbon atoms in a straight chain is called ethane. A alkane that has 3 carbon atoms in a row is going to have the prefix prop, and the name is propane. So now you can relate, oh wait, propane, like propane gas. Yes, it is an alkane. And you can see the structure of propane in that 3rd row. Now, the ones that are not Greek prefixes are 1 through 4, because on 4, as you can see, the prefix is bute. So you pronounce that as butane, not butane, okay? So for 4, the prefix is bute. The name of that alkane is butane, and you can see the structural formula given there. From 5 to 10, you guys, is all Greek prefixes. Pent, hex, hept, oct, non, dec. So we have pentane, hexane, heptane, octane, nonane, and lastly, decane, okay? So the molecular formula here that you see on the 4th column is given by the equation that I have here on the top. So let me just make that note. So this molecular formula is when we use CnH2n plus 2. And if N equals 1, you get CH4. If N equals 2, you get CH2H6. N equals 3, you get that one. N equals 4, so you can imagine as you go down, the number of carbons, okay, will also help you define the number of carbons and hydrogens. So all the way down to N equals 10, okay? Now, why are alkanes around us? Well, alkanes are actually nonpolar molecules that we can find them in crude oil, okay? So for those of you that drive cars that you have to put gasoline, okay, in it, think about it. There's our digits that are given at the gas station, depending on the number that you have to put in the gas tank. But that measurement, that it could be 89, it could be 91, it depends on the grade that you want your gasoline to fuel your car. But that measures the octane that is found in gasoline, okay? So if the word of the alkane, or sorry, if the name of the alkane is octane, how many carbon atoms do we have in the octane of gasoline? Let's put it in the chat. Great job, exactly, 8 carbons. So as you can see, alkanes, you may be using them and you didn't even realize that you were using them. Now, alkanes in general, because they have carbons and hydrogens in them, they are nonpolar molecules and they are insoluble in water. Now, one of the issues is that because they're nonpolar and also not soluble in water, when there are oil spills in the ocean, which is the image that you guys see on the right side of the slide, it is a problem because it creates contamination and it can actually affect the health of many marine animals. And because we can consume, for those of you that consume animals like, if you consume products like fish, if there is an oil spill, then that can affect, again, the health. Now, in oil spills, you can see that the oil is on top of the ocean, and you can see it there by those patches that look orange, because alkanes are known to be less dense than water. One of the concerns is that these molecules are actually flammable in air. So you can imagine that when this happens, there are many effects to nature, and that's why it's very important that these accidents do not happen often. Now we are going to look into how is it that we represent organic molecules, okay? So When it comes to organic molecules, we have a series of ways that we can illustrate them, starting with the molecular formula. So the molecular formula is what we have utilized to date to express how many carbons and how many hydrogens we have of a particular molecule, okay? So that we're familiar with. Then we have the ball and stick model. The ball and stick model is just illustrating to us what is going to be the arrangement of electrons around space for those carbons and hydrogen atoms that we have in a particular molecule. So you can see here that we have as an example, the molecule of hexane. Hexane has 6 carbons. Now, that ball and stick model, what it's showing you is that each one of those carbon atoms has a tetrahedral electron group geometry. So if we have a tetrahedral group geometry, what is the angle that separates the atoms in a tetrahedral molecule? Let's put it in the chat. What's the angle? Great job, 109.5. So that's why you see that in that ball and stick model, we don't write it as a straight line, because the angle that separates those hydrogen atoms or those single bonds between the carbon atoms in the context of an alkane is 109.5 degrees in the angle. So that's why you see it adopt that. All of that is computer generated, and we have some physical models that can illustrate that too. Now, we can also illustrate organic molecules in the expanded formula. So the expanded formula is nothing other than the Lewis structure that you guys have learned already. And you can see that in this Lewis structure is just a 2-dimensional representation of the number of carbon atoms that you have and the hydrogens that are there. It is important to note that when it comes to carbon, carbon is an atom that respects the octet rule. So make sure that you remember that carbon always has 8 electrons around it. It can come, as you can see here, as single bonds, and there's going to be different flavors as we progress in this chapter. But know that please do not put more than 8 electrons on carbon. Carbon is not one of those elements that can hold more than 8 electrons. Let's just limit carbon to have 8 electrons only. Now, we are going to graduate from the Lewis structure. When it comes to organic compounds, the most common ways in which we're going to see the drawings of our structures is going to be in the condensed formula and also the skeletal. Okay, those two. What is the condensed formula? Well, if we look at the expanded formula, you guys, the condensed formula is just bringing in the hydrogens that we had in the Lewis structure. So we can see that, for example, here we have a CH3. So that's exactly how we write it. Now, if this is written as H3C, it represents the same thing. So it doesn't matter if we write it as CH3 or H3C, we still are talking about the same unit in terms of the atoms that we have there. As you can see, here we have a CH2. Oh, this is the CH2. We have a CH2. Oh, that's the CH2. We have a CH2. There is a CH2. Another CH2. There's a CH2. And lastly, we have a CH3. That's where the CH3 comes from. Now, what is the skeletal formula? The skeletal formula is specifically illustrating how we have those different carbon atoms being separated by that 109.5 angle. So the skeletal formula is kind of like an interpretation of what we see from the ball and stick model. That's what it is. So it's related to this. How do we draw that skeletal formula? Understand that when it comes to this, in the skeletal formula for alkanes, we may not write in carbons or write in hydrogens. This is how you develop them. You're going to, with your writing utensil, you can put a dot, and that's going to be carbon 1. Here we're drawing hexane. So what you're going to do is that you're going to draw an angle pointing up. You could also do it pointing down, but here I chose to point up to illustrate the drawing that you see there. So we have carbon 1, we put you put a line going up, then you put a circle, that's carbon 2, down carbon 3, up carbon 4, down carbon 5, up carbon 6, okay? So I find that my students in Chemistry 112, sometimes those dots that we have there helps them better when drawing structures. So when you are, downloading and practicing at home, feel free to write those dots to symbolize these vertices that are created during the skeletal structure, okay? As I mentioned, if you start here, you can also say, okay, I'm going to point down carbon 2, up carbon 3, down carbon 4, up carbon 5, down carbon 6. It is the same structure, okay? Understand that all I did was that I made the bond go down. So when it comes to organic structures, it's always you're creating valleys and hills as you go along, okay? Any questions on how we represent organic molecules? Great. It is essential that we understand when it comes to organic compounds, that organic compounds can be divided into families, which we know as functional groups. And organic compounds, as you can see, are going to be big compounds made out of carbon. So carbon is going to be the atom that we focus on. We can find attached to atom hydrogens like we saw in the alkanes. But as we progress talking about organic chemistry in this chapter and future chapters, we're going to see that other nonmetals like oxygen, sulfur, nitrogen, phosphorus, or even halogens are going to be attached to carbons to give rise to organic compounds. The image that you guys see here on the top right corner of the slide, this is just a cartoon that was created by an artist, and it gave each of the elements in the periodic table a superhero identity, and this is the one for carbon. So carbon is a pure substance, and for example, diamonds are a pure form of carbon. That's why you see that in this superhero, the top part is diamond, and then you have charcoal and graphite, because those are also forms of carbon. Where do we see organic compounds? As you guys can see here, organic compounds are pretty much everywhere. In the clothes that you wear, in the shoes that you wear, in the medicines that you may take, in the food that are around us, in the plants, in the animals. So organic compounds are inside of us. That's why they are so important and why we are going to talk about them. We can find them in many products. They have low melting points and boiling points. Again, many organic compounds are not soluble in water. The ones that are, I will be specifying it as we talk about them along. And we are going to mainly be focusing on covalent compounds, because since carbon is a nonmetal and is interacting with other nonmetals, the compounds mainly that we're going to be seeing are covalent compounds. Now, when it comes to functional groups, it is important that we know the different functional groups that are present. And in order to ease the understanding of the functional group, I have actually separated them into families. As you can see, at first, we have the hydrocarbon family, we have the heteroatomic family, we also have the carbonyl group family. So next week on Tuesday, this is where we're going to start. Just understanding what are the different functional groups in organic chemistry, because once we understand that, then understand that we are going to identify those functional groups and some organic molecules that we have out there. Thank you so much for coming, you guys. This is all for tonight. Have a great rest of your week, and I hope to see you guys on Tuesday.